Alrighty. Hello, good morning, everybody. Welcome back to Abstract Algebra. Plan for today, we're going to continue our discussions of group homomorphisms. And I hope by the end of today, we get, after we talk about some properties, homomorphisms, and look at some examples that I had you all look at last time, plan to talk about isomorphisms, which is going to be the structure by which we can determine if two groups are actually mathematically the same, even if they look different. So we've got office hours this afternoon, 2 to 3. Tomorrow morning, 10 to 11. Tomorrow afternoon, 1:30 to 2:30. As a reminder, homework 4 is due tonight. And exam 1, which has been posted, is now due next Wednesday. So as a reminder for the exam, you're allowed to work with just one other person. As far as your solutions go, I would like for you to type them up, just like with the homeworks. I hope you like poker. There's a nice poker question on the exam. Any questions or comments before we get started for today? What do you call an angle that's been in an accident?
A rectangle.
Yeah, call it a rectangle. By the way, as a reminder, if you're working with other students in the class, please please make sure to social distancing, wear masks if you're working in person, etc. Do it safely. I feel like I need to say. All right, here we go. So last time we talked about what it means for a function between groups to be a group homomorphism. We said it's a homomorphism if you multiply two elements in the first, if you star two elements in the first group and then apply the function phi, we always need to get the same thing as if we had taken phi of g and phi of h individually and then applied the group operation from the second group. So operation in first group then phi, or phi and then operation in second group always comes out to the same thing if you have a group homomorphism. Basically a function that respects the group operations of both of the original two groups. And so I asked you to look at several different examples at the end of class last time for whether or not these are examples of group homomorphisms. And I thought we'd start off today by going through them and seeing what you all found. So what do you think about this one? We take the map phi from the integers to the reals that takes every single element in the integers and just maps it to 0. Is that a group homomorphism? Let's see. Well, if we were to take, for any two integers, x1 and x2, we would get phi of x1 plus x2, since the group operation in the integers is just addition. It's going to be phi is, well, x1 plus x2, like everything else, has to map to 0, which is indeed phi of x1 plus phi of x2. Where again, in the real numbers, since we're including 0, our group operation is addition in both groups. And so we do get that phi of x1 plus x2 is equal to phi of x1 plus phi of x2. Awesome possum. That's a group hom. Hom you'll sometimes hear as being a shortened form of homomorphism. The same argument can be used in any two groups. Given any two groups, you can always find at least one homomorphism between them. Given any G1 and G2 groups, you can always define a homomorphism from the first group to the second group by just mapping everything to the identity element of the second group. That's always going to be a group homomorphism. And we're going to call that map the trivial map. So just by mapping everything to the identity, mapping everything in the first group to the identity element of the second group is always going to give you a group homomorphism. So no matter what your two groups are, no matter what their group operations are, you always just say, and map it all to the identity. And you'll get a homomorphism, albeit one that's kind of boring. Called the trivial map because it's there, it's just not very interesting. Just like how, given any group, you can always take just the identity element, and that'll form a group called and that'll form a subgroup called the trivial group. And the trivial subgroup is always kind of, it is a subgroup, but it's not a very interesting one. You can't really do much with it. How about the second one? If we take the map psi from the integers to the reals, defined by you take an integer and you map it back to itself.
Yes, because they have the same operation.
They have the same operation, yeah, and that being addition. Because we can say, given any elements, d1 and d2 in the integers. Don't ask me why I went x1, x2, and g1, g2 here. I felt like it apparently. Psi of g1 plus g2, well, by definition, psi of anything is the same thing, which will give us psi of g1 plus psi of g2. So, map that maps everything to itself from the integers to the reals will give us a group homomorphism. How do you think we can generalize this one? We're able to generalize the first example by saying you can map between any two groups. Just if you map everything to the identity element of the second group, that'll give you a group homomorphism. How do you think we might be able to come up with a more general statement for what this example tells us?
Mapping any element to itself is a homomorphism if the two groups have the same operation.
Yeah, they have the same operation, or in particular, if the first group is a subgroup of the second group, I would say. Yeah, we can say that in general, we can say if H, let's say, is a subgroup of G, then the map psi, going from H to G, where we just take psi of any element H is the same element H, that's going to be a group homomorphism. And this one has a specific name. It's going to be called an embedding. Embedding sort of meaning like we're just kind of taking our subgroup H and we're wedging it into the group G, into a larger group G. And if we just take the identity map, the map that takes every element and maps it to itself, as long as H is a subgroup of G, that will form a group homomorphism. And here, H being a subgroup of G, we definitely are relying on the fact that that tells us H and G have the same group operation. How about this one? H of G is equal to G squared from the integers to the reals. Group homomorphism. Yeah, Mike?
It's not.
Gadzooks. How do we know it's not?
Because you have A, B, and the integers, A plus B squared is not equal to A squared.
Ooh, yeah. A plus B quantity squared is not equal to A squared plus B squared in general. I think there's a lot of textbooks out there that will call that the freshman mistake or something. Freshman exponentiation error. Unless you're working over Z mod PZ, in which case it is true. But we're not looking at that. So how can we come up with a specific, does anyone have a specific counterexample in mind that we can use to prove this? Because in general, it's not enough to just make a general claim that A plus B quantity squared is not equal to A squared plus B squared. Best way to, if we really want to disprove this, we need a specific counterexample to do it. Right?
You can use plus and minus 1.
Because, yes, that works. You say, did you just give me an example where it doesn't work out? Or where this actually does check out? No, you didn't. Okay, good. Yeah, if we take, this one is not going to be a HOM. And to disprove it, we only need a single pair of elements that doesn't satisfy this equation. And a good choice of elements, I would say, is 1 and negative 1. Because if we take h of 1 plus negative 1, well, that's just going to be h of 0, which is 0. The 0 squared is 0. But if we were to take h of 1 plus h of negative 1, that would give us 1 plus 1 is 2. Which is not the same as h of 1 plus negative 1. And since we can find a single pair of elements that makes that the group homomorphism equation not hold, that tells us this is not a group homomorphism. To disprove something, you just need a single counterexample like this. You need a single counterexample, but to prove it, we needed to prove in full generality here. It wouldn't be enough to just say psi of 1 plus negative 1 is equal to psi of 1 plus psi of negative 1 to prove we have a group homomorphism. To prove it's a homomorphism, we would need to show it for every possible pair of elements, which is why we do it with an arbitrary G. But this next one, K of G, hey, that's my initials. We take the same map, we take an element in and we square it, but this time we're looking at two different groups. The reals under multiplication, the non-zero reals under multiplication to the non-zero reals under multiplication. Now think about this one. Y'all are just going to be quiet. Let's do it by a show of thumbs up. Thumbs up for group homomorphism, thumbs down for not one. A little bit of controversy. Callie apparently is shifting her vote. Gabe, why do you say yeah?
I don't remember. I wrote no question mark and then I wrote yes and then I circled it.
There you go. Well, that sounds like a more emphatic yes than an emphatic no.
Wouldn't it be a group because it's all like the order of multiplication doesn't matter? So whether it's like AA times BB or AB, it all equal each other.
Yeah, it ultimately comes down to the fact that A squared times B squared is always going to be equal to AB quantity squared. We're working over an abelian group. So in this one, we can say given any G1 and G2 in our group of non-zero reals, we could say that K of G1 times G2, and here we have to keep in mind our group operation in the first group is multiplication, not addition. K of G1, G2 is by definition just going to be G1, G2 quantity squared. Well, that's going to be the same as G1 squared, G2 squared. Because technically this, all right, fine, let's do it this way. G1, G2, G1, G2, which is G1 squared, G2 squared. If we use associativity and commutativity, both of which are things that we have in this group, which is equal to K of G1 times K of G2. What valuable lesson have we learned from the last two examples? Lessons we have learned. Yeah, right?
Not the operation so much as the groups that you're looking at.
I would say it's both. Both are very important. Is that we can have the same function, or the function doing the same essential thing, in this case taking something from the first group and just squaring it. But depending on which groups you're looking at, depending on the group operations at play, a function might be a homomorphism between two groups, in this case here, that is not a homomorphism between two other groups. So it's not just enough to look at the function, what the function does to say if it's a homomorphism or not. We need to actually look at how does the function relate to the group structures in play. All right, awesome. Let's do some, got a few more here. How about this next one? We take alpha from GL2R to the non-zero reals, where alpha of matrix A is defined to be the determinant of A. By show of thumbs, thumbs up for group homomorphism, thumbs down for not a homomorphism. Hesitant thumbs, people waiting to see what other people are doing before committing to a thumb. Yeah, so it turns out for this one, I think is going to be a group homomorphism because given any two matrices, A and B, in GL2R, if we were to take alpha of A times B, well, that's just going to be the determinant of A times B, which, using a fancy property of determinants from linear algebra, is going to be equal to the determinant of A times the determinant of B, and which will be equal to alpha of A times alpha of B. Or if you notice, our group operation is different between the two groups. In the first group, our operation is matrix multiplication, so matrix A times matrix B. But in the second group, our operation is just real number multiplication. And so alpha of A times alpha of B is just taking two real numbers and multiplying them together. So we have different group operations here, but alpha does respect the group operation. Pays its respects. And so we do, in fact, satisfy the group homomorphism equation here. Questions or comments? Before we move on? All right, which one's next? Ooh, one using some recent groups. How about the map beta that starts in the symmetric group on n elements and ends up in the alternating group on n elements? Remember, A sub n is just the set of all even permutations in Sn. Where we took beta of gamma and spat out gamma squared. Sort of like what was happening in the last two examples. Show of thumbs, yay or nay? Ooh, I like this one. I see some thumbs up, some thumbs down, and some thumbs sideways. Nick, what are your thoughts?
Well, I'm questioning them now, but I was thinking, so if you took 1, 2, and 3, 2 as your A and B.
Okay, let's say we'll have a sigma is equal to 1, 2, and tau is equal to, what's your other one?
3, 2.
3, 2. Don't be a barbarian. 2, 3. You claim,
So if you do beta of 1, 2 times beta of 3, 2, then both of those will be the identity. So you just end up with the identity.
okay, so let's see. That'll give us 1, 2 squared times 2, 3 squared, which will be, yeah, just the identity.
But then maybe I did it wrong, but if you do them as one unit, 1, 2 times 3, 2, then I didn't complete the calculation, but I did get the identity out of it.
Oh, you didn't complete it, huh?
Well,
Let's see.
Yeah.
Well, let's see. We take beta of sigma times beta of tau. Is everyone okay with that coming out to the identity element, since 1, 2 squared is the identity, 2, 3 squared is the identity? Let's see. If we were to multiply and then apply beta, that would be, all right, 1 maps to 2, 2 maps to 3, 3 maps to 2, which maps to 1. So that would be beta of 1, 2, 3. And I do believe 1, 2, 3 squared can give us 1, 3, 2. Sorry, thumbs uppers, I think I agree on this one. This one is not going to be a group homomorphism. Another scenario where the squaring map turns out to not be a homomorphism due to the kind of the group structures of the groups we're applying this, of the group elements we're applying this map to. And finally, and this one was my favorite, gamma from D3 to D4, gamma of x equals x. So map R to R, R squared to R squared, RS to RS, etc. Show of thumbs. Thumbs up or thumbs down? Everyone who's willing to take a stand is giving it a thumbs down. Elaine, why'd you give it a thumbs down?
I'm so confused. I'm honestly trying to figure out what the alternating group is right now.
So the alternating group
Black
AN,
problem.
that's just that was the set of all even permutations. So the set of all permutations in Sn that you could write as a product, as in product of an even number of two cycles.
Okay.
So something like these would not be an A sub n because they're odd permutations. They're just written as 1, 2 cycle. But something like 1, 2 times 2, 3 would be an even number of two cycles. So that would be what's in the alternating group. Yeah. We kind of touched on that one a little bit on at the end of the last packet. We're going to see a lot more of the alternating group once we get to the packet after this one, in fact. So gamma of x equals x. Oh gosh, I'm starting to do the same thing as my OTA, starting to mix up my Greek letters, calling everything sigma. Gamma of x equals x. Here's a fun twist. I agree it's not a group homomorphism, but I'll take you one step further and say that's not even a function. Right?
R is not the same thing in both.
Yeah, for one, R is not the same thing in both groups. Like just saying, oh, map R to R, well, you're saying map a 120-degree rotation of a triangle to a 90-degree rotation of a square. That's not the same thing. Right?
I don't know if you can use the R's and the S's for X because they're functions, not values.
Well, we could just say it's a function that maps one function to another function. I mean, technically, that's what we were doing in our last example. Here, sigma and tau were actually themselves functions. The function that swaps 1 and 2, the function that swaps 2 and 3. And this actually worked out okay as a function. Beta actually worked out okay as a function. It just wasn't a group homomorphism. So it's okay to have a function that's a function that you plug in functions and get new functions. So functionception. That's actually something that's generally okay to do. The issue in this case is, what would we get if we took gamma of R cubed? Well, according to the definition of what this is, that should just give us R cubed, right? In the group D4. You're wrong, because clearly R cubed in D3 is the identity element, and so that should map to the identity element. So clearly, the identity element has to be equal to R cubed in D4. If this is a function, which it is not. So a function, when we say it's not even a function, what that means is the same elements in one group can map to multiple things in the other group. And that something like that is no bueno, not a function. The same element, R cubed, as an element in D3, is being mapped to multiple elements in D4. So gamma cannot be a well-defined function. And since it's not even a function, it's not a homomorphism either. So, very subtle reason. This is not technically the identity map in the same way that like the second example we looked at, the embedding was an identity map. Since D3 and D4 are inherently different groups with a different group structure to it, composition of symmetries of a square versus composition of symmetries of a triangle, you can't actually define this and call it a nice behaved function. Questions or comments about any of these examples? Okay, so before we move on to isomorphisms, I want to take a little bit of time and talk about a couple of different subgroups that are going to get associated to the original groups with the homomorphism. I think you were asking me about this last time. And that is the idea of what is the image of the homomorphism and the kernel of the homomorphism. So in general, we can say that for any group homomorphism, phi going from group G1 to G2, we could talk about the kernel and the image of this map, in which we say that the kernel of phi, which we define to be the set of all elements G in the first group, such that phi of G is equal to E2, where E2 is what we assume to be the identity element of the second group. I claim that forms a subgroup of G1 called the kernel of G1. So you all should have taken linear algebra. And when you took linear algebra, do you remember hearing about like the kernel of a linear transformation? Is that something that came up? Not really? Okay. Well, I've never taught linear here, so it's someone else's fault. Well, here's a fun twist. You all remember talking about linear transformations? Linear transformation is just a group homomorphism between vector spaces. All linear transformations are just going to be to individual types of group homomorphisms. If you look like you're about to take outrage at that.
Well, isn't there also a requirement on like scalar multiples for a linear transformation?
Yeah, technically vectors. Yeah, technically there are examples of ring homomorphisms, which is something we haven't talked about yet, where we have a multiplication and an addition where we have two separate operations going on. You're right. There are also examples of group homomorphisms. Okay. There are group homomorphisms with some extra stuff attached to it, I will say, which we'll see in a couple months from now once we get to rings. So I claim that forms a subgroup of G1 called the kernel, and there's another subgroup that's associated with this called the image, where we can define the image of phi, which is going to be the set of all elements in the second group. Set of all elements of our second group, such that H equals phi of G for some G and G. In other words, the range of phi, you may have seen this before, the set of all things that are actually getting mapped to by something, that's always going to form a subgroup of G2. And that'll be the image of G1, or the image of phi. What did I say the kernel? Why am I saying the kernel of the kernel of the map? So the kernel of phi and the image of phi, if we're looking at phi being a group homomorphism, I claim are always going to give us subgroups. Like the set of all things mapping to the identity element is going to be a subgroup of G1, and the set of all things in the second group that are actually getting mapped to by something is going to be a subgroup of G2. Let's look at a few examples and see if we can evaluate what's the kernel, what's the image. So let's say we have a function f that goes from some group G to the same group G. And let's say that map is the identity map. What's going to be the kernel of this map? In other words, which elements in our first group are going to get mapped to the identity element of the second group?
The identity element?
That's just the identity element of the first group. I'm going to put it as E1. Since E1 is the only element that's going to satisfy P of E, or not P, F of E1 is equal to E2. We're here. Actually, you know what? I don't need to say E1 because it's the same group. The only element in G that's mapping to the identity element, well, by definition, is just the identity element itself. If every element maps to itself, then what maps to the identity? Only the identity. Therefore, the set containing the identity element is going to be the kernel of this homomorphism, which is going to be a subgroup of G. What's the image of this map going to be? In other words, which elements in the group G are getting mapped to by something from G? Right?
All of them?
All of them, because everything's getting mapped to by itself. Since every element in G gets mapped to by the same thing. So in this case, we find that the kernel is only the identity element. The image of our homomorphism is the entire group. And hey, that's kind of cool. Both of these are subgroups of G. I want you to take a couple minutes and see if you can figure out what the kernel and the image are of the last two homomorphisms on this page. So in other words, the map that sends everything to the identity and the map that takes any integer and multiplies it by n. Go ahead and take just a minute and see if you can determine what you think the kernel and the image are of these two bottom functions.
Okay, so it's part of the same group. So
For the first
we
one,
want the identity, so we want it to be the identity of the second group, but I mean, they're the same group. So
Hi, Lauren.
can't he,
hope you could remember it.
for the kernel, yeah.
I'm getting that it's, for the second one, that's everything.
For those of you taking this class remotely, I encourage you, as always, to try these exercises out for yourself before you skip ahead in the video and just see what the answer is. Try for yourself. Good practice.
Yeah.
It's the sort of thing I'm likely to ask on a homework or exam in the future.
And it's not equal to.
It's the things that are like a range.
Would it be just like,
I really enjoy class.
hold on, this has
Oh,
to
so it's all the things.
be addition.
So it's E, it can only be E.
The real numbers are
Okay.
multiplication,
What
right?
about the first, what about the first one?
No, they're addition to it. Because you don't get inverse from zero again.
The kernel is
You're right.
If you take away 0, the group operation
Okay,
is
so it's-
typically multiplication. If you include 0, the group operation is going to have to be
Okay,
addition.
the third one.
Whether it's the integers or the real or the
So, can I just take this
Is the image just?
So the identity element of the R
Is
zero.
Right.
So
The real numbers are, okay, so the image is within the real numbers, right? So we make it for the integer, because we're getting an integer.
Well, n is constant, so it's gonna be nx for all x within the integers, I think.
And what's the image then?
Because it's not gonna match every integer, say, if n was 2, then it's just gonna be all even integers. Yeah, and that will include 0.
Is it
So
V?
X can be zero.
And I'm pretty sure the kernel is just the identity,
But they have to
because
be the
same thing with 0. If you put 0 as the identity for the first
Oh,
one,
you're
if
right.
you put that in, you're just gonna get n times 0, which is just gonna be 0. So, true. It's pretty cool.
So it just be the identity.
Oh, you.
In which case
And
it
the
would be
image, I
like
think, is based on the X, so it's,
Which
It's gotta be
would
nx.
yeah.
For all x and z.
No, I think NC, I have no idea.
Because NC ends up being.
Yeah.
I can say.
Make sure you specify the x and z.
Assuming you're looking at a group after we do these people, we're gonna talk a little bit about.
Yeah, I think it's just the identity again, because
If you have a group homomorphism, which all three of these
the
are,
identity, the second one is
every
0.
example, every time you took a kernel or the should form a subgroup of the
For the image.
Did you just get the image?
So the image says that what you get from G1, you plug into the
Well,
function.
it's the integers, but
Is the
only the
same
ones
as
that are
A.
divisible
Oh.
by n.
So the image is the same.
No.
So the way we wrote it was nx for all,
Yeah, no,
for
never
all
mind.
x in the integers.
You don't have to do that.
So R would be like. It's contained in Greek, it's not all, so you're not gonna get.
No.
You won't get 5 once in like a weird thing. Well, can you equal it's empty, but it's possible, but if you can get 5.
As always, if you have questions you want to ask me as I walk around the room, feel free to flag me down.
Okay.
But that's true.
Interesting.
And I learn.
Yeah.
When's the kernel ever not
I do too.
identity?
We're down 8 students now.
In the second one. Well, right, but that's because it is the identity.
Well, 7 if you don't include the student who's who's taking the entire class remotely from the start.
So, yeah, just a question for this. The kernel is inputs would give you the identity element.
Yep.
Yeah, well, and it's the.
Like, they're kind of buried here.
Really hard on this, but anyone's
Let's say n is 2. After the x is 2 times. I think you can still find something that'll map to the identity element.
It involves photographic popcorn.
We're always gonna get something, it just might not be very much.
Yeah, but that'll always be enough.
Kind of like in our first example with the identity map, only the identity itself maps to the identity.
Is n an integer or just any constant?
It doesn't mean it has to be whole.
Softball team started doing that.
Oh.
Well,
that's.
Sorry, I should specify, typically whenever you see me write n is always gonna refer to an integer.
Yeah, no, it's big R.
It doesn't actually change, I don't think that your answers really change very much. If n is an integer or,
Because it could be like, you could get like pi, 2 pi, 3 pi, like integer pi, something like
or just integer multiples of 5, that would work.
that. Is that a proper notation of like pi z?
Easy. Eyes. Yes, that would be fine.
Okay. Well, you're right.
It would be a little bit non-standard because usually when you write in something in the form nz, you're talking about a cyclic subgroup of the integers. And pi z is very much not a subgroup of the integers. In fact, there is, other than pi times 0, there is no element in common with pi z and the integers.
So you almost want to specify that n would be an R if that was the case.
Yeah, I mean, yes. The answer to this doesn't really change very much by specifying anything for themselves. All right, everybody's gotten quiet, so let's do this. Little g maps everything to the identity. What's going to be the kernel of this homomorphism?
The identity?
Oh, the identity is certainly in there because the identity will match the identity. I think there might be a little bit more to it though. Yes?
G.
It's going to be the entire group.
Oh, we're doing the second one. Good.
Oh yeah. The first one is just the identity, and the second one, if everything maps to the identity, then by definition, the kernel has to be the entire group. How about the image of this map? Just going to be the set containing the identity element. Because the only thing that's getting mapped to in G, the only thing that's getting mapped to is the identity element by definition of the map. So this one's sort of like the reverse of the first example we looked at. And that this time the kernel is the entire group and the image only consists of the identity element. But just like in the previous example, both of these are going to be subgroups of G. The improper subgroup and the trivial subgroup, respectively, but not interesting ones. All right, here's one with a couple specific groups. The function f going from the integers to the reals that takes an integer in x and spits out n times x for some non-zero integer n. So if n is not equal to 0, what's the kernel of this map going to look like?
It's 0.
It's just going to be the set containing 0, which is technically different than just saying 0. 0 is not a subgroup. 0 is not a group at all. But the set containing 0 here, the trivial subgroup of Z, once again, will be the kernel. Because if we assume that n is not equal to 0, then n times x can only be equal to the identity of R, which is 0, if x itself, the input, is 0. What's the image of f going to be? In other words, what is the set of all outputs going to look like? Right?
We said nx for all x in the integers.
Like that?
Yeah.
Anybody have a snazzier way of saying this? Group?
Ouch.
Heard people over here talking about it earlier. Nick?
NZ.
We can also just call this NZ. Or if we really want to be cheeky, subgroup, the group generated by n as a subgroup of the reals. However you want to call it, this will give us a subgroup of our codomain. It's going to be a subgroup of the real numbers. And so kernel and image are just finding them, and it's just kind of doing this thing where you see what maps the identity in the first group, and what are the things in the second group that actually get mapped to by something in the first group. 6 minutes, that's time for one of them. All right. I will now prove one of these two things does indeed form a subgroup of the thing I claim it's a subgroup of. Stephanie. Which one don't look too excited. Which one would you like to see? Proof of kernel being a subgroup or image being a subgroup?
Kernel.
Thank you, that's the one I took notes for. So let's prove the kernel of a group homomorphism does actually give us a subgroup. Also, by the way, Stephanie, you just now made it so that the image is going to be a question on the next homework. Thank you. If you don't like the next homework, it's her fault.
You think I would know it that long?
All right, so here's the proof. All right, so here's the theorem. I didn't give you a space to write this because I didn't decide to do this until after I'd already printed these packets out. So write this wherever you want, if you want to write it. Let's say if B from G1 to G2 is a group homomorphism, then the kernel of B is a subgroup of G1. Here's my proof. Oh, hey, subgroup. We have lots of theorems that determine when something is a subgroup. I'm going to use the two-step subgroup test. So, because by the two-step subgroup test, all I have to do is to show that the kernel has closure and that it contains inverses. But I also need to show something a little bit more insidious. Something that's not obvious. I also need to show that the kernel is not empty. that there is at least one element in the kernel. Because if you recall, in order to be able to use either of our subgroup tests, we needed to assume that the set we're starting with is non-empty. So if we want to show kernel phi is a subgroup of G1, what element might be a good idea to try and show is going to be in the kernel? Right? Let's show that the identity element in G1 is in the kernel. So first of all, we'll prove the kernel is not empty. So I need to show that phi of the identity element in the first group has to be equal to, so we want to show this, that this is equal to E2, the identity element in the second group. Check this out. Instead of taking just phi of E1, let's get fancy and take phi of E1 is equal to phi of E1 times E1. Is everyone okay with that? That the identity element in G1 times itself is itself? The identity element. You multiply by anything, you'll get the other thing. So if you multiply itself, you'll get itself. Well, since phi is a group homomorphism, that's going to be equal to phi of E1 times phi of E1. And then we can just apply the cancellation law and cancel out a phi of E1 on each side, and that'll just leave us with phi of E1 has to be the identity. Thus, by cancellation, phi of E1 is going to be equal to the identity. And hence, E1 is always going to be an image, or is going to be an element of the kernel. Because we get phi of E1 times phi of E1 is equal to phi of E1. Do a little swoosh swoosh, cancel out a phi of E1 on both sides. Phi of E1 has to be the identity element of the second group. And so the identity element in the first group is always going to be an element of the kernel. So the kernel is always going to be non-empty, in other words, which is something that's necessary for subgroup. So next up, I'm going to prove closure. I'm going to prove it with a nice sized piece of chalk. Didn't crack, still a nice sized piece of chalk. So now, to prove closure, we need to show if we take two things in the kernel and multiply them together, that we're still going to get something in the kernel. So we're going to let, let's call it A and B, the elements of the kernel of B. And our goal is going to be to show A times B also has to be in the kernel. Well, if A and B are individually in the kernel, then we can say that phi of A times B is going to be equal to phi of A times phi of B. Here using the fact that phi is the group homomorphism. Well, phi of A times phi of B, well, that's just the identity element times the identity element. Since A and B are in the kernel, that means phi of A and phi of B have to be equal to E2. So the E2 times E2 is still going to be E2. Hence, AB is also going to be in the kernel of B. So if A and B are individually in the kernel, then A times B is also going to be in the kernel. Sorry, I got a little fast, but we're running a little over time. And finally, we need to show inverses. So now, I'm going to let G be in the kernel of B. And our goal is then going to be to show that G inverse also has to be in the kernel. Well, if we take phi of G inverse, that's going to be phi of G inverse times the identity element in the second group. It's because the identity element times anything is that same thing. Well, we know a little something about E2. Since G is in the kernel, E2 has to be phi of G, by definition, of G being in the kernel. But since phi is a homomorphism, This is just phi of G inverse G. But we know something about G inverse G. That's just going to be the identity element in our first proof. And what did we know about phi of E1? Boop, 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 boop. It's E2. So then that's going to tell us, since phi of G inverse has to match to the identity in the second group, that's going to tell us that G inverse is in the kernel. Plus, by the two-step subgroup test, the kernel of B is in fact going to be a subgroup of G1. Sorry, I had to kind of rush this proof a little bit because we were running out of time. Happy to go back through each part of it if you feel stuck. Contact me. Happy to meet with you in office hours. You can go through this if you feel like you've fun. All right. That's going to do it for today. On Friday, we are finally going to talk about isomorphisms, which are homomorphisms with the twist. Have a good day.